Hello and welcome to the 14th webinar in our Lunch, Learn and Dance Wellness webinar series, all about airborne mining hazards. Joining me in the chat room is Maria Costa. Anastasia from Salem Dance Company will be leading us in dance beginning at 12:30 Eastern. Let's take a moment to go over the functionality of the Zoom webinar. The audio and video will be from the presenters only. We have found that although you can access the audio through the computer or telephone, the quality of sounds tend to be better when listening from a computer. There is a chat feature where people can discuss. If you would like, take a moment now to say hello and where you are from. If you have questions arriving from the content, please enter them under the Q&A section. As the webinar is only a half hour in length and is immediately followed by our dance session, time may not permit for me to answer them during the webinar. The answers will be posted on our website, along with a link to the video recording and a copy of the slides. This can be found under Education Webinars. I will be sending a confirmation of attendance email after the webinar and will include a link to the page with that communication, along with additional resources. I will also include the topics covered and the length of time spent in the webinar, as some people have requested this to send to the professional association. Lastly, I have automatic closed captioning enabled in the slide presentation. If they are being blocked by your Zoom controls, you should be able to select a different way to view the webinar in Zoom, which makes them easier to see. In the webinar, we will first outline mining health and safety hazards, focusing on airborne hazards. We will then look at what health effects can occur from exposure to the substances. We will finish up with a word about regulation, detection, and where to get more information on mitigation strategies used to keep workers safe. You may be wondering why the Radiation Safety Institute is doing a webinar on airborne hazards in mining. So we'll begin with an explanation of this choice of topic. In December of 2013, Ontario's Minister of Labour asked the Chief Prevention Officer to undertake a comprehensive review of the occupational health, safety, and prevention issues related to underground mining in the province of Ontario. As a result, the Mining Health, Safety, and Prevention Review was launched in January of 2014. The review followed a consulting process that involved labour, employers, government, health and safety partners, the public, and content experts, and included extensive review of the data and experience in other jurisdictions. The review identified 6 key health and safety issues in underground mining. Within the health and safety hazards issues, 5 key hazards were identified as being those that pose the greatest risk to health and safety. They are ground control, including the risks associated with seismic activity and rock bursts, occupational disease, focusing particularly on exposure to airborne hazards, water management, particularly problematic water in ore and waste passages, mobile equipment and risk of collisions, and worker fatigue. This webinar focuses on the second point, the exposure to airborne hazards that may result in occupational disease, such as asthma, COPD, pneumoconiosis, silicosis, and various forms of cancer. To help address key health and safety hazards in Ontario's underground mines, the review developed a series of recommendations geared to strengthen existing legislation, encourage the development and adoption of best practices and new technology, and to help focus the efforts of the Mining Legislative Review Committee on the highest risk health and safety hazards in the mining sector. Within the airborne hazards area, the review identified 5 priority hazards, including silica, nitrogen dioxide, diesel particulate matter, sulfur dioxide, and radon gas. As a result of this review, the Radiation Safety Institute of Canada developed a free online course on this topic in partnership with the Canadian Centre for Occupational Health and Safety, CCOHS, and Morocco Mining Innovation. The development of this course was funded in part by the Ontario Ministry of Labour. It focuses on silica, diesel particulate matter, and radon gas in detail. To access the course, visit onlinelearning.radiationsafety.ca. I will include a link in the mailing, but if you have any difficulties finding this, please feel free to contact me. We will begin and look at all the different materials that could cause airborne hazards in mines, and then we will go on to the health effects and then connect the two. Coal is a type of sedimentary rock formed when wetland vegetation is compressed in a low oxygen environment over tens to hundreds of millions of years by layers of sediment. It contains carbon and is burned to produce heat. It is used in many countries to generate electricity. As it is mined, coal dust is generated. The diesel engine is the most efficient power plant among all known types of internal combustion engines. Heavy trucks, urban buses, and industrial equipment are powered almost exclusively by diesel engines all over the world. Diesel engines are easier to maintain and generally have lower operating costs than their gasoline-fueled internal combustion counterpart. In addition, diesel engines are more robust than most other engines and have shown the ability to sustain high performance in physically harsh environments. As such, since their introduction to mining operations in the 1960s, diesel equipment has become increasingly employed and recognized as the workhorse in mining. By mass, most diesel particulate matter, or soot, is composed of fine or ultrafine carbon-based particles. These base particles are surrounded by bound or suspended hydrocarbons, along with inorganic components such as sulfates and ash, and metal oxides from lubricants such as lube oil and additives. In fact, as shown in the slides picture, the particles have hundreds of chemicals adsorbed, which means stuck to their surfaces, including many known or suspected carcinogens and mutagens. A mutagen is a chemical agent that changes or mutates genetic material, while a carcinogen is a chemical agent that causes cancer. The physical and chemical composition of diesel particulate matter depends on the physical and chemical processes that occur in the engine and in the atmosphere after their release. Typically, diesel soot particles range in size from 0.05 to 0.25 microns, with an average diameter of about 0.15 microns. There are 1,000 microns in 1 millimeter. Metals are elements found on the left-hand side of the periodic table, beginning with the dark gray section shown. Their properties include being good conductors, ductile, and malleable. They can be found as a pure element or in a compound, amalgam, solution, or alloy. Metalliferous mine dust is mine dust that contains metal. Common metallic elements found in metalliferous mine dust are shown. The reference paper, Metalliferous Mine Dust, Human Health Impacts and the Potential Determinants of Disease in Mining Communities, states, epidemiological and toxicological studies have indicated that the hazard posed by mineral dust depends not only on their abundance and particle size, but other properties such as their chemical composition, solubility, shape, structure, and surface area of the inhaled particles, which all play a role in the associated toxic, carcinogenic, or other health effects. In mining, nitrogen dioxide is found as a component of diesel exhaust or the result of blasting. It is a toxic substance which is difficult to notice in your surroundings. Depending upon the temperature, it can be found as a colorless solid, a yellow liquid, or a reddish-brown gas. It is a corrosive acid. Radon is a naturally occurring radioactive gas which is formed from the radioactive decay of uranium. As uranium is present pretty much everywhere, at least in small quantities, radon is also found all over the world. Radon is a colorless and odorless noble gas that does not chemically react with other elements and which tends to accumulate in enclosed spaces. It has a half-life of 3.8 days and emits radiation when it decays. Although radon gas is of some concern, of more concern are the radioactive elements formed after radon decays, called radon daughter products or radon progeny. The decay chain after radon has many radioactive atoms. For health effects, we are mainly concerned with the short-lived radon daughters that form after radon itself decays. Unlike the radon gas, these daughters are solids, metals in fact, which tend to attach themselves to dust particles in the environment once they are formed. When the radon progeny attached to dust particles are inhaled, they tend to remain in the lungs until they decay. Two of these daughters emit high energy radiation. This slide pictorially shows the short-lived radon daughters or radon progeny. Shown here are the first 5 radioactive atoms that form after radon decays and which are the ones considered for health effects. Two of these emit alpha particles, which are high energy radiation that do not travel far, so therefore are only of concern if inside the body. There are a few more radon daughter products after the series shown, but they are not as much of a concern for health effects and are therefore generally not discussed. Radon can enter a mine via groundwater. Radon is soluble in water and tends to hitch a ride, so to speak, in flowing groundwater. If that groundwater flows into a mine, the radon gas comes with it, and once in the mine, particularly if the water is agitated, like flowing over a bumpy floor, the radon easily escapes the water and enters the mine air. Once radon gas is airborne, it can decay to form radon daughters, which attach themselves to dust particles in the air. The concentration of radon gas, and thus radon daughters, in a mine can vary depending upon many factors. The amount of uranium in nearby rock will affect how much radon is generated and can reach the mine. The amount of groundwater flowing into a mine can also affect radon gas concentrations, as can ventilation in the mine and environmental conditions such as air temperature and humidity. Although radon gas has a short half-life and quickly forms radon daughters, which also quickly decay away, radon is constantly being renewed into mine air from the surrounding rock and soil, so it is a continual concern. Silica is a chemical compound which is formed from atoms of silicon and oxygen. It is commonly found in the form of silicon dioxide, or SiO2. Silica exists naturally on the Earth's surface in forms such as quartz and silica sand, and can also be produced biologically by tiny organisms such as diatoms, which extract silica from the water surrounding the organisms in order to form their structures or shells. When the silica compound is created, it can end up with a solid structure that is either crystalline or non-crystalline, sometimes called amorphous. In the crystalline state, the atoms and molecules make up a three-dimensional repeating pattern. The pattern unit is repeated continuously in all three dimensions, forming a crystalline structure. The pattern unit is not necessarily the same in all crystalline forms, but within a form, the pattern is repeated identically. Quartz is an example of this crystalline form of silica. In the non-crystalline form, atoms and molecules are not organized in a continued repeating format. They may have some patterns that repeat for a short distance, but they do not repeat the pattern in all dimensions of the material. Diamantite is an example of an amorphous form of silica. There are three common forms of crystalline silica, including quartz, cristobalite, and tridymite. Each of these forms is stable under different thermal conditions. Various processes, including foundry processes, burning of waste materials, and other manufacturing processes, can cause quartz to change form. In nature, quartz is the most common form, although lightning strikes can cause quartz to change into different forms of silica. Quartz is very abundant, found on every continent in large quantities. All soil contains at least trace amounts of quartz, and quartz is used commonly in many industries. Silica should not be confused with the element silicon, nor with silicates or silicones. Silicates are minerals made from silica, but also containing other elements such as sodium, potassium, or calcium, to name a few. Silicates are the most commonly found class of minerals, being the basic materials out of which most rocks are created. Some silicates are very valuable, for example, emeralds. Silicones, on the other hand, are synthetic polymers that are created from two or more silicon atoms, linked with carbon compounds and also usually containing oxygen. Silicones can range from liquids or gases to resins and solids. All soil contains at least trace amounts of quartz, and it can be found in most types of rocks. Igneous rocks are rocks that are formed when magma from the Earth's molten core pushes to the surface of the planet and solidifies. Sedimentary rocks are those formed by loose minerals when they accumulate in a basin and are solidified. Metamorphic rocks are formed through heat and/or pressure. Quartz is abundant in all three types of rock. As crystalline silica, or quartz, is such a common component in rocks, mine workers are potentially exposed to it in airborne dust when rocks is cut, drilled, crushed, and transported. Typically, one finds medium to high concentrations of crystalline silica in ores of uranium, gold, and copper. Lower concentrations are found in nickel and iron ores, and even less in coal and limestone. Any material with more than 1% silica is considered to be hazardous. Silica can be found in many forms, ranging from large rocks and stones to powders to microscopic particles that cannot be seen by the eye. In fact, the particles of silica that are of concern for breathing into the lung, called respirable sized particles, are less than 10 microns in diameter and cannot be seen by the eye. So we cannot rely on seeing dust to determine if we're protected or not. Silica is found in many occupations, not just mining. Exposure to silica must be controlled in all industries where it occurs, including working with gemstones or other high-quality quartz crystals, working with silica flour, for example, in the creation of paints, and where silica sand exists, such as in glass making, foundry molds, and the making of concrete. In mining, sulfur dioxide is generated from the sulfur present in diesel fuel during combustion and during the smelting of mineral ores that contain sulfur. It is easily dissolved in water to form sulfuric acid. While not contributors to long-term health conditions, there are many gases which can be of concern in mining due to their explosive nature, their toxicity, or their tendency to displace oxygen, which can cause asphyxiation. Prominent examples are shown in the table. Now that we have outlined numerous airborne hazards in mining environments, we will look at some of the diseases which can result due to exposure and then connect which hazard is associated with which health condition. As children, we often drew pictures of the lungs as being two empty bags that would get larger and smaller as we breathe. And while they do expand and contract during breathing, the lungs are far from empty and not the only part of the story on how we breathe. The respiratory system in humans includes the nose, mouth, throat, voice box, windpipe or trachea, and the lungs. The trachea branches in two, one branch for each lung, and further branches within the lung. The large airways of the lungs are called the bronchi, which branch into smaller airways called the bronchioles. At the end of the bronchioles are air sacs called alveoli. The alveoli throughout the lungs are surrounded by the smallest of blood vessels, the capillaries. The walls of the alveoli and capillaries are thin enough that gas exchange between the blood in the capillaries and the air in the lungs can occur. The main gas exchange needed to occur for humans to live is to release carbon dioxide from the blood into the air in the lungs and to move oxygen from the air into the blood. So rather than being like two empty balloons, our lungs are living tissue with incredible surface area, between 50 to 75 square meters or 540 to 810 square feet. The more surface area, the more opportunity for the gas exchange to occur. The bronchi of the lungs also have hair-like structures called cilia to sweep debris and microscopic organisms up and out of the airways. The respiratory system has other mechanisms to keep the lungs clean, including the production of mucus and coughing. This diagram shows where the different sized particles can reach into our respiratory system. Particles of 5 microns or larger deposit in the sinuses, nose, and throat. Particles down to about 1 micron in diameter can reach into the bronchi of the lungs, while particles smaller than 1 micron in diameter can reach the end of the bronchi and bronchioles and reach the alveoli. Gases and extremely fine particles can fully perfuse the lungs, reaching the alveoli, and have the potential to enter the bloodstream. We use the term particulate matter, or PM, for a mixture of solid particles and liquid droplets in the air. There are many types of individual particulate matter that cannot be seen by the naked eye, as the smallest particle that can be seen by the eye is about 50 microns in size. Human hair is approximately 50 to 70 microns thick. This diagram shows the relative size of various particles in human hair. PM 2.5 particles are 20 times smaller than are visible to humans, and ultrafine particles, or UFPs, are more than 500 times smaller than what the human eye can see. So the air can appear to be clean, but still contain particles and gases dangerous to human health. We will now go through lung conditions which can be caused by these materials. For a person with asthma, an attack can be triggered by allergens such as pollen or pet dander, particulate matter such as smoke, dust or exhaust fumes, or environmental factors such as exercise or exposure to cold air. During an attack, the muscles which wrap around the airways constrict more than they should, and for many people, their lungs produce more mucus than would be expected, which restricts further the already constricted airway. A person who is having an asthma attack will have symptoms like shortness of breath, chest pain, wheezing, and coughing. This could be a minor irritation for someone who is having a mild asthma attack to something deadly. While many people with asthma develop symptoms in childhood, adults develop asthma as well. There are drugs which can help manage asthma, but as of yet, there is no cure. COPD stands for chronic obstructive pulmonary disorder. It is a group of chronic inflammatory diseases of the lungs, most commonly emphysema and chronic bronchitis. In a person with COPD, the alveoli are slowly destroyed, which reduces the amount of surface area available for gas exchange in the lungs. Inflammation and narrowing of the bronchial tubes cause mucus buildup. The most common cause of COPD in Canada is cigarette smoking, but chemical fumes and long-term exposure to air pollution and dust are also causes. People who have a genetic deficiency called alpha-1 antitrypsin may be at higher risk of developing COPD. Symptoms are similar to asthma, but are not in the form of attacks. The symptoms start off gradually and become progressively worse over the long term if the condition is not properly managed. Treatments include lifestyle changes, medications, oxygen therapy, and surgery, depending upon the stage of the disease. Pneumoconiosis means lung disease caused by dust. It is a broad group of lung diseases caused by the inhalation of particulate matter, typically mineral dust, but also things like cotton or other fibers. If your lungs are exposed to dust over years, it can cause inflammation and scarring. This causes a loss of blood vessels and alveoli. Pneumoconiosis is a type of interstitial lung disease. Interstitial tissues are found in an organ or tissue, but not a defining characteristic of that organ or tissue, for example, connective tissue. The lungs gradually lose elasticity, resulting in symptoms of shortness of breath, chronic cough, and weakness. Symptoms can range from no measurable impairment of lung function to death within months or years. Many kinds of rock and minerals can cause pneumoconiosis. Such rock is stable and insoluble and cannot be dissolved or removed by protective cells in the lungs and accumulate in the lungs over time. Depending upon the dust being inhaled, there are different forms of the disease. Common forms are silicosis, asbestosis, and coal workers' pneumoconiosis or black lung, shown as an image of slate pneumoconiosis. To compare, in a normal chest X-ray, areas which contain mostly air appear dark, while structures such as bones appear white. Silicosis is a form of pneumoconiosis, but is much more serious than most other types. When respirable-sized crystalline silica dust travel deep into the lungs, the sharp edges of these particles cut and irritate the cells of the alveoli. Lung cells surround and try to isolate these particles to protect the alveoli cells. This causes nodules to form, made up of cells and silica particles. These nodules continue to grow as exposure continues. As a result, the lungs become scarred and less flexible. Silicosis is fairly slow to develop, so that signs and symptoms may not appear for many years after the exposure. The first symptom of silicosis is usually difficulty in breathing that is first noticed due to exercise or other exertion. However, even when no symptoms or minimal symptoms exist, a chest X-ray may show the fibrous nodules or lung scarring due to silicosis. Often, such an X-ray is required to diagnose the disease. There are 3 forms of silicosis that a worker may develop, depending upon the airborne concentrations of respirable crystalline silica that he or she was exposed to. These include chronic silicosis, accelerated silicosis, and acute silicosis. It is important to note that there's no cure for silicosis once it occurs, and the damage done to the lungs cannot be reversed. Treatment of the disease, once diagnosed, can only try to reduce symptoms and prevent complications. We will now quickly explain what cancer is and how it is caused. The basic unit of life is the cell. Inside the cell are structures called chromosomes. They carry instructions for life processes, including replication. This information is encoded in smaller parts of chromosomes called genes. These structures are made up of a complex molecule called DNA. Some agents in the environment, such as chemicals or ionizing radiation, can interact with DNA and break bonds within the DNA molecule. These breaks can also happen randomly during cell division. While the body has processes to repair such damage, if repaired incorrectly, such a break could potentially change the instructions encoded in the genes. This is called a mutation. Mutations are not guaranteed to happen. When an environmental agent, which can break DNA bonds, interacts with a cell, there are several different outcomes which can occur. There could be no damage at all. There could be damage that is then repaired by the cell, and there could be damage which leads to cell death. This may sound bad, but unless this happens in large amounts, it is not of concern, as cells routinely die in small numbers. Environmental agents or cell division can also lead to an alteration of cell chromosomes that is incorrectly repaired, which is called a mutation. Because DNA carries instructions for cell replication, a mutation can change how a cell replicates. This can produce a mass of cells called a tumor. If a tumor does not spread to other tissues, it is called benign. If a tumor grows into surrounding tissues, it is called malignant or cancer. Malignant tumors can eventually spread to other parts of the body. Their uncontrolled growth uses up the body's resources and interferes with the functions of organs in the area where they grow. Please note that not all DNA mutations lead to tumor growth, as they could occur in a portion of the DNA which is not related to cell division or kill the cell. The development of cancer is called carcinogenesis. An agent known to cause cancer is called a carcinogen. The International Agency for Research on Cancer maintains a compilation of monographs on agents it has examined as possible carcinogens. They each cause cancer through one or more of the mechanisms shown here. Substances known to cause cancer are called Class 1. Airborne hazards in mining environments categorized as Class 1 include chromium-6 compounds, nickel compounds, arsenic and inorganic arsenic compounds, silica dust, crystalline in the form of quartz or cristobalite, and radon-222 and its decay products. As you can see, there are many mechanisms by which a substance can cause cancer, and sometimes a mutation which might lead to cancer can happen just through regular cell division. People can inherit DNA that already has mutations from normal. The body has processes by which it attempts to prevent cancer. Because of how many factors are involved in the development and prevention of cancer, if someone gets cancer, it is not possible to pinpoint exactly what caused it. An example is lung cancer. You may know people who smoke a lot and never get lung cancer. Some people get lung cancer and have never smoked. But if we look at a population of smokers versus non-smokers or never smokers, there will be fewer people in the non-smoker, never smoker group who get lung cancer. Smoking raises the risk of getting lung cancer, but smoking does not guarantee you will get it. When something increases in probability as a certain factor is increased, we call it a stochastic effect. Exposure to Class 1 carcinogens due to the airborne hazards in mining is stochastic. The increasing cancer rate by exposure will depend on what carcinogen is being considered. Now that we have overviewed airborne hazards in mines, related lung conditions, and cancer, we need to connect which condition is typical of exposure to which airborne hazard. Coal dust is mainly associated with coal workers' pneumoconiosis, also known as black lung, and COPD. Diesel exhaust is a known carcinogen linked to lung cancer and possibly bladder cancer. It can also aggravate heart conditions and respiratory illnesses such as asthma. Metalliferous mine dust is varied in composition and its effect vary by type of metal. Some are potentially toxic with toxicity ranging widely. Some cause inflammation of the lungs and some are known carcinogens. Nitrogen dioxide can aggravate lung conditions such as asthma or COPD. Radon is the second leading cause of lung cancer. Exposure to silica dust can cause silicosis, lung cancer, susceptibility to tuberculosis infection, and or inflammatory diseases such as kidney disease and rheumatoid arthritis. Sulfur dioxide is an irritant to many tissues of the respiratory system, the skin, and the eyes. Exposure can lead to coughing and shortness of breath, increased asthma symptoms, and respiratory inflammation. I know I'm going over time, but I promise it will be no more than 5 minutes, and then we'll move to dance. Mining health and safety is regulated at the provincial and territorial level, with the exception of the mining radioactive ores, which is federally regulated. In mechanized mines, diesel is seen as the large pressure or stress on mine ventilation systems. Many provinces require use of certified engines underground, and this is reflected in the regulations. As an example of how regulations can vary in Canada, we will look in more detail about diesel exhaust. In the early 1990s, the curtailment and control of diesel emissions in hard rock mines received significant attention in North America. In 1995, the American Conference of Governmental Industrial Hygienists recommended a threshold level value of 0.15 milligram per cubic meter for diesel exhaust particulate matter concentrations. In subsequent years, this TLV value was modified to 0.05 milligrams per cubic meter and then lowered again to 0.02. This proposed TLV regulation was a catalyst in terms of seeking technology and strategy to achieve such reductions in diesel particulate matter or DPM limits. In Canada, DPM regulations are mandated by each individual province or territory. The status of DPM exposures as compiled in 2015 are shown. Because air that appears to be clean to our eyes can contain damaging particulate matter and gases, part of a hazard control strategy is monitoring. They're part of a robust health and safety program and not a standalone measure. Air sampling can be static or personal. A static sampler remains in an area and exposure is calculated based on concentrations and the time spent in the area. Personal sampling is when a worker has a device which monitors their exposure throughout the workday. There are a number of international standards available with information on dust sampling procedures and determining concentration levels, and these may be referred to in regulation and legislation. As one example, we'll discuss detection for radon gas. There are a few different ways to measure radon daughters or progeny. A short-term sample is basically a grab sample where a pump is used to draw air through a filter and airborne dust containing radon daughters is deposited on the filter. The filter is then placed within an instrument that can detect alpha radiation, where it is measured. An equation using the airflow rate of the pump are used to calculate the radon daughter concentration. Long-term samples can also be obtained in a similar way to the short-term samples using a filter and an air pump. But because the radon daughters decay so quickly, a special alpha-sensitive detector has to be put in place above the filter to detect any alpha radiation that is emitted over time. This detector is then sent to a laboratory for processing to determine the radon daughter concentration. Electronic monitors can also be purchased to monitor air for radon progeny, although they are quite complicated and expensive pieces of equipment. These units can generally measure and track radon progeny concentrations over time and are often set up with audible and visual alarms that activate if the concentration exceeds a predetermined set point. Finally, there's individual dosimetry for radon progeny. Individual radon progeny dosimeters measure the total exposure to radon daughters over a specific amount of time. When workers start their shifts, they take a personal alpha dosimetry unit out of its charging rack and attach it to their belt or shoulder strap. They wear it during their shift, and its internal pump samples the air and collects airborne dust on the filter. An internal detector, very much like a detector for the long-term sample discussed in the last slide, detects the alphas emitted from the filter. When workers are done their shift, they put the unit back in the charging rack to recharge. At the end of every month, the internal detector head is removed and sent to a laboratory for processing. The Radiation Safety Institute of Canada supplies this licensed service to uranium miners in Canada. The Institute was also recently part of a research study on personal alpha dosimetry for non-uranium underground mines in Ontario using these devices. Protection measures vary by airborne hazard, but all aspects of the mining process need to be considered, including mine and mill design, mining methods, ventilation, workplace monitoring, and operational controls and work procedures. As we do not have enough time to go through all aspects of health and safety for all mining work sites, we'll point out some sources for information, which will be compiled and posted on the webinar section of the website with a link emailed out. The Canadian Centre for Occupational Health and Safety has relevant fact sheets and online training. Morocco Mining Innovation is the non-for-profit mining research arm of Laurentian University. Their mission is to be the innovative research partner of choice for mining and related industries. They also provide workshops and other resources to those in the mining industry. One of our partners in health and safety, Workplace Safety North, hosts an annual mining health and safety conference. Proceedings of past conferences are available on their website. The Occupational Research Cancer Center has fact sheets on carcinogens found in mining. They estimate 220 lung cancers and 20 suspected bladder cancers per year in Canadian miners can be attributed to occupational exposure to diesel exhaust. 80 lung cancers attributed to exposure to silica and 20 due to radon. They also have available a document produced in 2017 outlining strategies to control diesel particulate matter in underground mines, ranging from elimination through to PPE. The Mining Association of Canada participates in their Towards Sustainable Mining, or TSM, initiative. To quote their 2019 highlights publication, the TSM is an award-winning performance system that helps mining communities evaluate and manage their environmental and social responsibilities. It is a set of tools and indicators to drive performance and ensures that key mining risks are managed responsibly at participating mining and metallurgical facilities, end quote. One aspect of this initiative is safety and health, which would encompass mitigation of airborne hazards. Canada's nuclear regulator, the CNSC, has information on radon gas in mining, along with many other resources. The National Institute for the Occupational Safety and Health, a branch of the US CDC, has several published resources to assist the mining industry to control dust and diesel exposure. The Government of Western Australia also has a number of English resources regarding air quality and ventilation in underground workplaces. We hope you found this webinar on airborne hazards in mining informative. If you have questions about health and safety in mining, we will put you in touch with someone who can help based on your occupation and region. If you have questions about radon in mines or any other radiation safety topic, please feel free to contact us at the Radiation Safety Institute of Canada. We have a toll-free information service to support questions from employers, workers, and the public with respect to both ionizing and non-ionizing radiation safety. We also provide consulting services for those who might need support in developing a radiation safety protection program and related services, including radiation surveys. If you have any further questions about ionizing or non-ionizing radiation, please feel free to contact us toll-free at 1-800-263-5803 or by email at info@radiationsafety.ca. You can also visit us on the web at www.radiationsafety.ca or find us on Facebook.
To register, go to www.radiationsafety.ca/services/webinars.